smart streetlight pole. Top battery placement caused wind load issues. Inside the pole, there isn't enough space. Underground costs and construction needs exceed the budget. 3 options. None of them are perfect. In this video, I want to clarify the real costs of these 3 options. Not to tell you which one to choose, but to help you navigate real project constraints and make a more accurate decision. Battery selection for traditional solar lights is very simple. Fixed power consumption, match the capacity, put it in the pole compartment, and you're done. But smart streetlights are different. When a single pole integrates AI cameras, LED screens, environmental sensors, emergency calls, and 5G micro base station systems, power consumption can jump 3 to 5 times. Battery capacity must increase too. Then the limitations of the 3 locations are fully exposed. This is very clear in South America. Many projects face high wind speeds and long off-grid runtime requirements. Combining these 2 factors makes battery capacity and installation needs much stricter. Option 1. Inside the pole. This is the global mainstream. It looks clean and resists theft. Well, no civil work is needed, but space is a hard constraint. Most standard smart pole cavities don't have space for large batteries. Many projects discover only at delivery that batteries won't fit the compartment. This physical conflict roots from one key issue: equipment choices disconnected from pole design. They weren't aligned early on, even if squeezed in. Heat is the next big issue. According to IEA data, the ideal temperature is 15 to 35 degrees Celsius. Sealed metal enclosures under direct sunlight in northern Chile or northeast Brazil can easily overshoot this range. Constant heat accelerates capacity decay. Actual lifespan falls below the rated value. Internal options suit low power systems and early design stages where space compatibility is confirmed. Beyond this, you must reevaluate. Option 2. Pole top exterior. This is usually a compromise solution. It won't fit inside the pole, and civil work isn't an option. Its flexibility is real, but the structural risks are much larger than expected. Crucially, wind load impact on top equipment is entirely non-linear. According to ASCE, wind load design standards, adding weight to the top magnifies wind area and lever arm length. When these variables combine, the base bending moment amplification is not just 1 plus 1. It scales non-linearly. European pole standards are also strict. They require specific checks for top attachments. Simply put, choosing top mounts in high wind zones means you need a full pole structural redesign. It is not just a minor adjustment. If the original pole lacks margin, you might need a higher spec pole. For central southern Chile, Argentinian Patagonia, and coastal Peru, you must calculate these conditions early. This is not a detail to ignore. Option 3. Underground battery pit. Underground fixes wind load issues. It also solves space limits. Weight shifts below the surface. The pole returns to normal stress levels. Soil temperatures are more stable. This helps extend battery life. But the costs are real. Civil costs come from 3 parts: excavation and backfilling, waterproof load structures, and design for maintenance access. Underpaved roads. Construction costs spike further. These costs depend heavily on geology and local markets. You must budget them separately early on. Waterproofing and corrosion protection are vital. IP67 is the minimum. Coastal projects need IP68. The South American Pacific coast is C4 to C5. Metal components must be treated properly. Next is maintenance design. This is the most ignored step. Batteries last 3 to 5 years. Then they need a full replacement. If the underground pit isn't well planned during design about how to swap them, how to handle drainage, or monitor faults remotely, future maintenance costs will ruin the project economics. Many underground plans fail, but not from quality. It is because designers skipped one critical question: How do we swap this battery in 3 to 5 years? These three options. None is a silver bullet. Internal options, phase space, and heat limits. Top mounts bring structural risks in wind zones. Underground brings civil costs and maintenance hurdles. In my view, this must be decided in the design phase, not after the equipment arrives. Deciding after arrival multiplies the cost of every choice. If you are reviewing similar projects, let's discuss it below.